In the very last presentation, we introduced the tuned mesh dampers, which helps Taipei 101 overcome the issues regarding earthquake. Other than the TMDs, there are structural solutions selected for the building to meet the seismic challenges. They are core bracing, outriggers, super columns, and perimeter moment frames with reduced beam sections. Overturning stiffness is enhanced by outriggers in two directions. A mix of single and double-story outriggers are distributed every 8 to 10 floors along the building height. On each building face, they engage two vertical super columns located to clear facade setbacks. A perimeter moment frame follows each sloping building face, and core beams are designed and detailed to function as moment frame members. Highly articulated facade planes, core bracing, outriggers, super columns, and perimeter frames complicated the flow of forces among these disparate elements under gravity and later loads. As for outrigger and super columns, which are outrigger systems, we have already explained them in details as structural resisting later forces in presentation before. Today, we are going to introduce the remaining structures, which will be core bracing and perimeter moment frames. We are also going to explain how all the structures work together. Before we get into the details, there is an important thing we have to keep in mind. Wind and earthquake both were the issues when designing Taipei 101. Design for stiffness against the wind was considered, and then ductility and seismic strength followed. It was because considering earthquake in the first place would cause a problem of the building not being able to withstand the wind. To resist the later loads, there are three major structures that are used: brace frame, shower, and moment-resisting frame. Among these, most efficient way to resist earthquake in particular is brace frame. Frame bracing can be divided into two major groups according to their appearance: EBF, eccentric braced frame, and CBF, concentric braced frame. The difference is how braces are connected. CBFs are connected to the node of the joint of the frame, while EBFs are connected at a certain distance from the node of the frame, meaning link is used as you can see here. Concentric braced frame has two groups again: ordinary concentric braced frame and special concentric braced frame. In the case of Taipei 101, special concentric braced frame takes place between these two. Comparing these is important in the case of skyscrapers like Taipei 101. Their configurations are same. Braces basically withstand tension and compression as the later loads are applied. But the difference is in the design philosophy. To just simply say the difference, special CBF is designed focused on ductility, and the ordinary CBF is designed focused on stiffness and strength, minimizing an inelastic demand. Then, which one is better for Taipei 101? To answer this question, we have to look from the very bottom of the line, the most fundamental purpose of seismic design. It is to prevent building from collapse in the maximum considered earthquake and to shake less. To achieve this, ductility and elastic deformation is the key. Ensuring inelasticity, we can design for much smaller earthquake forces and provide necessary ductility capacity. And this is how the prevention of the collapse is ensured. This leads us to the conclusion that special CBF with greater ductility works much better for Taipei 101 than ordinary CBF. Now, let's go back to the diagram and talk mainly about eccentric braced frame and special concentric braced frame. Eccentric braced frame is developed relatively recently, combining advantages of concentric braced frame and momentum frame, which are both used to resist later loads. As I mentioned before, link is the biggest difference that you can notice at one glance. Link is the short segment between two braces member connection. It functions to absorb the energy dissipation and to control inelastic deformation, resulting in structural stability. To say it simply, links in eccentric braced frames provide the ductile behavior and counteract the impact of the seismic forces. This seems to fit perfectly to the explanation that I gave earlier. The importance of ductility to withstand the earthquake. But interesting fact is that concentric braced frame is the kind that is mainly used in Taipei 101, not eccentric braced frame. Why is this? All the reasons lay on links. Links can work negatively to skyscrapers sometimes. They could make the frame too soft, where stiffness can be neglected in tall buildings. So, Taipei 101 uses concentric braced frames, which can be described as a frame with strengthened links. More to this, concentric braced frames are economical compared to the eccentric braced frames. A strong earthquake is expected to cause plastic hinges at the end of the beam in a fully restrained momentum frame. To counteract these plastic hinges, the connection between beam and column in the momentum frame must be stronger than beam. To solve this problem, previously the method of reinforcing a momentum connection was used. However, there were disadvantages of using this method, such as requiring too large a load and increasing the cost. The structure of Taipei 101 uses a reduced beam section that looked like a dog bone to address these shortcomings. The reduced beam section, as the name suggests, removes a part of the beam flange. At first glance, it may seem counterintuitive that removing a portion of a structure actually improves the performance of the structure. In the case of the dog bone, however, this is exactly the case. The dog bone results in only a small reduction in lateral strength and stiffness of a frame, but can provide a large increase in ductility, the key to survival of a structure in a strong earthquake. Trading a small amount of strength in return for a large amount of ductility represents an excellent bargain for earthquake-resistant design. In the front of this video, we mentioned the solutions selected for the building to meet the seismic challenges: core bracing, outriggers, super columns, and perimeter moment frames. Braced core, outriggers, super columns is grouped as outrigger system. Braced core and perimeter moment frame is called special moment resisting frame (SMRF). By code, a building of this height requires a dual system for lateral loads, which is outrigger system and special moment resisting frame. Steel moment frames along each sloping face of the building work in parallel with the braced core and outriggers against lateral load. In the video before, outrigger system is already mentioned. In outrigger system, the moment generated to the core is transferred to super column by outrigger trusses, increasing the moment arm. The moment is effectively resisted. Through the rigid joint between steel girder, beam, and steel column, the core withstands the lateral load and uplifting moment in each module. Setbacks from the sloping facet would interrupt moment frame following the building face, which causes the ineffectiveness under vertical load even its own weight. Gravity load in these frames transfers to main outrigger columns by belt trusses at the bottom of each module. Today, we are talking about braced frames and moment frames that are used in Taipei 101. They especially all contribute to resist earthquake. Next week, we are going to talk about pinnacle fabric next week. Thank you.